Hey everyone, welcome to The Explainer. So today we're taking a look at what I think is the ultimate engineering magic trick. I want you to just picture this for a second. You've got a 20-ton piece of flying metal, packed to the brim with jet fuel and explosive weaponry, screaming through the sky at supersonic speeds, and yet to a radar operator sitting at a screen, it's completely invisible. No way, right? How do you actually make a modern fighter jet just disappear? Well, today we're going to break down the rigorous, honestly mind-bending physics that makes stealth technology possible.
Check out this quote. An F-22 has the radar signature of a mosquito. Really think about that for a second. A mosquito. We are talking about a machine that is over 60 feet long, built entirely for war, and yet it registers on these highly advanced tracking systems as a tiny, insignificant little bug. It's wild. Today we're going to unpack the exact science behind how they pull this off.
So here's our roadmap for the explainer today. 1. The foundation of stealth, radar cross-section. 2. Geometric shaping methods. 3. Surface currents and calculations. 4. A quick comparison of the F-22 and F-35. And 5. Engine intakes and the Lüneburg lens. Let's dive right in.
All right, Section 1. The foundation of stealth, radar cross-section.
Now, the core problem we're dealing with here is that radars emit electromagnetic waves. When those waves hit a highly conductive surface, like, say, the metal skin of an airplane, they bounce right back to the receiver, immediately giving away the plane's position. So, to really understand stealth, you have to understand this one crucial metric: radar cross-section, or RCS. Put simply, it's just a measure of how effectively a target reflects a radar signal back to where it came from. Large passenger planes, they have these massive flat surfaces, so their RCS is huge. They act like giant mirrors in the sky. For stealth aircraft, the entire game, the whole shebang, is about reducing this RCS parameter to the absolute minimum.
And this visualization right here brilliantly illustrates what happens when you don't design for a low RCS. Notice those massive, chaotic red spikes surrounding this conventional, non-stealth B-26 bomber. Because a standard older aircraft has all these complex, blocky shapes facing in totally different directions, its radar footprint is just huge. And worse, it changes randomly at almost every angle as it flies. It is literally a giant, chaotic beacon in the sky.
Moving on to Section 2, Geometric Shaping Methods.
So to stop that massive bounce back, the very first step in our illusionist playbook is macro-level design. We have to fundamentally change the actual physical shape of the aircraft. Notice the comparison here between basic geometric shapes and aircraft design principles. On the left, you can see that curved shapes, like an ogive, exhibit a much lower RCS than a flat cone. Engineers take these exact principles and scale them up to the whole jet. They sweep the leading edges of the wings back, they blend the components together so perfectly smoothly, and they get rid of any external bumps. They even hide all the missiles and bombs inside internal bays. The entire goal here is to angle all the surfaces so they deflect that scattered radar energy away from the enemy's receiver.
And when you look at the historical timeline of stealth aircraft, you can really see how this idea evolved over time. Early on, like with the F-117 Nighthawk, the shaping was highly faceted and blocky, just lots of sharp, flat panels. Why? Well, because early computers in the 70s and 80s could only calculate radar reflections for flat surfaces. But as supercomputers evolved, so did the geometry. We moved from that blocky F-117 to the incredibly smooth, blended, almost organic forms of the B-2 Spirit, the F-22 Raptor, and the F-35.
Okay, Section 3, Surface Currents and Calculations.
Here's the catch, though. Modifying the aircraft shape is awesome, but the plane still needs to actually, fly. Aerodynamics are a thing. So, when geometric shaping alone isn't enough, we have to zoom in to the micro level. We have to control what happens when radar waves actually hit the skin of the aircraft. This is where radar-absorbing materials, or RAM, come into play, and it's fascinating. First up is impedance matching. The surface of the plane is engineered to match the electrical resistance of the air itself, which is around 377 ohms. This basically tricks the radar wave into entering the material instead of bouncing off. Then, once it's inside, materials like microscopic iron spheres or carbon nanotubes create what's called dielectric or magnetic loss. Guys, it literally turns the electromagnetic energy into heat through microscopic friction. And finally, they use a Salisbury screen, a geometric trap where the radar wave reflects inside the coating and cancels itself out through destructive interference. It works exactly like the noise-canceling headphones you might be wearing right now, but for radar.
Now, as you can probably guess, engineering all of this requires some insane computing power. To understand exactly where radar energy builds up, engineers use a mathematical technique called domain decomposition, What they do is have supercomputers break the F-22's complex geometry down into these distinct, colorful mathematical chunks. The front fuselage, middle fuselage, back fuselage, and so on. By breaking it into pieces like this, they can run complex integral equations to simulate exactly how surface currents will behave across the whole jet.
And the result of those massive calculations is this right here, a map of induced surface currents. Notice the warmer colors on the model. That's highlighting exactly where electromagnetic energy is pulling up, like along the sharp edges of the wings or right on the nose. Having this map is a total game changer because it allows engineers to perfectly tweak the geometry or apply thicker radar-absorbing materials exactly where they are needed most.
All right, Section 4, F-22 and F-35 comparison.
So we've covered a lot of really dense physics, from macrogeometric shaping down to domain decomposition. But what does this actually achieve out in the real world? Let's look at the scoreboard. This table is just mind-blowing. Look at the older generation F-4 Phantom II. It has a massive frontal radar cross-section of 6 square meters. Now compare that to the 5th generation fighters we've been talking about. The F-35A drops all the way down to 0.00143 square meters. And the F-22 Raptor? An absolutely unbelievable 0.0018 square meters. That right there, that is the mosquito we talked about at the very beginning. It completely proves just how effective a balanced combination of shaping and absorbing materials can be. And finally, Section 5, engine intakes and the Lüneburg lens.
Now, there is one major vulnerability we haven't talked about yet, and it's notoriously the most challenging part of any plane to hide. I'm talking about the engine intakes. Jet engines require massive amounts of air, which means you essentially need big open holes in the front of the plane. And remember how I said flat metal bounces radar perfectly? Well, spinning metal turbine blades are basically radar mirrors. To solve this, engineers curve the intake ducts into an S shape and line the insides with radar-absorbing materials. So radar waves enter the duct, bounce off the curved walls, lose energy with every single bounce, and completely dissipate before they ever reach the actual engine turbine. It's like a high-tech, dead-end labyrinth for electromagnetic waves.
Okay, now let me pose a highly counterintuitive question to you all. You've just spent billions of dollars and decades of rigorous engineering to make a fighter jet completely invisible to radar. Why on earth would you intentionally bolt a device onto it to make it visible again?
Well, the answer is right there inside those red circles, the Lüneburg lens. See, during peacetime flights, regular training, or flying near civilian airports, being completely invisible is actually a huge safety hazard for air traffic control. Plus, militaries actively want to hide their true stealth capabilities from any enemy surveillance that might be gathering intelligence during peacetime. So they attach these small radar reflectors, the Lüneburg lenses. They deliberately spoof the aircraft's RCS, making this cutting-edge F-35 look like a massive glowing blip on a civilian radar screen, safely hiding its true invisible signature until it's actually needed for combat. So, as we wrap up today's explainer, I really want you to take this away. Stealth is not magic. From the macro-level geometry of swept wings to the microscopic molecular heat transfer of surface currents, making a 20-ton jet disappear is pure, rigorous engineering. It is this intricate, beautiful dance of deflecting, trapping, and absorbing energy.
But, technology never stands still. As radar systems continue to evolve with advanced infrared sensors and their own massive supercomputers, you have to wonder, will this illusionist's playbook be enough to keep the skies silent in the decades to come? It's a fascinating, endless cat-and-mouse game of military engineering. Thank you so much for joining me on this explainer, and keep questioning the science behind the magic.